Can I minimize Zoom? Why not? Oh, okay, I'll do this. So for programming assignment, there was a mistake, typo mistake in the default value for M. It was M2 and 3, it's M3 and 6. If you have to. Now, please read what you have to submit. It is very instructions. All right. For example, if you have submitted your assignment, which I think 5 of you did, and you miss submitting the M file, you're going to lose points. Okay. So the M file is the default value, or if we needed to check your, so the PDF is showing you have results, everything is good, if you have the answer, and if everything was good, now if something doesn't look good or right, and we're like, oh, this I don't do, there's something happening here, you're gonna run the M file. Okay, so make sure you always send the M file. Now, yes.
Is that the M file with user input or without user input?
So M file is what you use to run to create the published version of the PDF.
So the one with default value.
Yeah, it has to have default value. So what we do, if we need it, we will uncomment the part that you're asking our user what to do. Make sense? So don't forget, if you did, can you still submit to the deadline is on it? Yeah.
So basically, we need to put the two files.
Basically, it's the sum of two files. Oh, wow.
PDF,
Yeah. And your PDF cannot be generated by the Word file convert to PDF. It has to come from that. The whole point of this assignment is to learn the process, because this assignment itself is not difficult. It's one formula, getting some input, doing all that inside, and then submit. So everyone's code will have 3 different distinct sections. Input, default values, whatever, always. Then, so you have some constants sometimes. You put them in that section. Then you have your equations. Solving dynamics, kinematics, and ever. That's the middle section, right? Then you have result or output section. So we're trying to learn the structure of the report. So please don't miss any part and read this properly. Again, the goal was not what you're doing in it, like what more editing and reporting. And you can get help from these, but if you don't know how to publish, you can read that. It's pretty straightforward. You cannot get help on this one, like reuse something, or you can get help. Sorry, you can get help from other classmates or us, but you cannot find. Oh, I have a code. Make sense? You can submit as many as you want. Means that because you have different options, it could be text upload, online. This is a file. Okay. So we have a technical problem. If you're walking, deal with it. Echo, because I can never send this to the busy to fix it.
it might be.
Amazing. Yeah. And I lost the thing I put in there. I know, not gonna work. Anyway, let's try this. All right, so let's go to previous lecture, solve the example, and then come back to the example. All right, so this one. Everybody open this, and I don't look at that. Oh, why it's not there? Because I didn't do that. All right. So go grab the formula and solve this one. I'll walk around, see what you're doing. I'll give you 5 minutes. All right. Yes, your demand. Yes. You should get an extra point for this. So all right, so this one is since we already you guys hear me? So since we already solved that one, so kind of should be familiar with this one. But this is a case of overlapping links, meaning that one link is connected to multiple links. And we will only count the link one time, as we counted from one time. So this link in the middle is connected to the three other links, will only count it once. And that's the only special thing about this example. So this is panel, and is 3, and is the ground is 1, 2, 3, 4, 5, is 6, 8, R, 7, and sigma F2 is also 7, and we have freedom will be 7, which is 1. No, so we got that. All right, so pay attention to that. Now, so when we were solving this example, I got to this point, but then it came back. That's exactly why. This was not always a bad thing, it's a design. Now let's go to this example. So sometimes you can solve the mechanism to find the degree of freedom in different ways. So you can have different approaches. You can mix two joints together to become the design. Okay, so let's check this mechanism down below. So let's first identify all the joints. Here is a revolute joint. Here's a revolute joint. But you have a revolute prismatic. One thing I want you to pay attention is that this prismatic joint is a sliding on one link, right? Goes from one side to the other. You could have a case of a prismatic joint that's connected to two links. Can somebody bring an example? Who bites here? suspension, right? So piston, any piston, it is a prismatic joint, but you have two links moving. So if you had a piston, even though it's prismatic, it's different from the slider case. Usually pistons are shown as such. So this is one link, this is one link, because they're both moving. You can change. One could be fixed, but it could be in a mechanism that's moving, right? So we will count those as two links, but here, since this is slider, is just a sliding along one membrane, it's only one. Okay. All right. Now try to find the geofreedom of this one. Based on what I explained, you should be able to do it. There's a prismatic joint, revolute. You have a ground. This is basically one link. You also have headphones. Who has a headphone? No? Okay. So if you're watching this video, there's going to be echo. I just have to plug the headphones so this does not pick up my voice from people. Oh, thank you. Also, what's your name? Adnan? Okay. Yeah, I cannot, both. Or that, it's any, I just need to, yeah. Thanks. Whew. Yeah, I cannot. Turn this off completely. Don't forget to take it from me. All right, you're solving this. Again, don't look at them. Are you waiting for me to solve? I'll work on it again. Are you done? Okay.
N equals 3 with a 10, and I was really
Oh.
confused.
Correct? That's what you got? So this is one way to approach this. All right? And it's totally fine. Because you're not changing anything. Now, if you look at this prismatic on the revolute, it could be a combined one. It could be, again, assume this is a box that's moving and also rotating. So in that case, we can solve it in a different way. The degree of freedom is similar. We can think of this as, well, this part is the same. This part is the same. This part could be, right? There's ground. You see that I'm not eliminating the rod, I'm just saying it's inside that box. Okay? Now, this joint is a PR joint. It has a degree of freedom in like a prismatic and also rotate. So it could have been something like this in reality, and you composed it to that diagram. So this would be a PR joint. This is R joint. This is R. Now when I'm counting, this is ground, D. Well, don't do that. 2, 3. All right. So we are not counting the rod inside because we are using the combination as one joint, right? So PR means that this has the ability to move inside. Now, M is 3, N is also 3, 1, 2, 3. What is J? You have 2R plus 1 PR. So you have 3 joints, but when you look at Fi, it's 2 times 1 plus 1 times 2 because PR has 2 degrees of freedom because it's like a cylinder cylindrical joint. Now, if you find the DOF from the formula, you'll still get 1. is also okay. All right. So if you realize you're trying to design something, you see a joint that can be decomposed, do that, and then we'll talk to you. Okay. So these are the two examples that was given from last lecture. Now, I will post some practice problems. You'll see different kind of joints. If you have the book look through, your next homework, well, your first homework is going to have some bigger freedom questions, right? So it's these same technicals, just practice from your book. Fine. Now let's go back. Let's go to today's lecture. Okay, that's one practice problem. This is in 3D. You have never done 3D before, right? You've been doing 3D. There isn't much of a big difference. What's going to be your M? 6. Okay? The default freedom is going to be 6. Now look at this. Joints. Here, right? If you remember from the table. And R is your volute. So each of these legs, each of these legs, an origin and origin, you see that this is repeated. So when you find the degree of freedom here, hint is going to be more than 6. All right, and then we can discuss like why. I want you to work on this, and on Friday we're going to visit this. So try to have an explanation why more than 6 degree of freedom, whatever number that is, makes sense or doesn't make sense. All right, then we can discuss them. So visit on Friday. I will not post. You can work on Friday. Sweet. Okay, now we're just getting into actual discourse. So far, it was just the definition and making sure that you have some prerequisite knowledge. Now, today we'll talk about rigid body transformation, which is composed of rotation and translation. We will also get to rotation matrix. Now, so what does transformation mean? It doesn't mean like transform the robot to a car. Which it was, it's not. The transformation doesn't mean look at me like that. You know. So for transformation, we will either rotate a rigid body or translate it. So that's really more here. Transformation, translation, and rotation. So translation is different from translation. Now look at this rigid body, this gray area. So if there was a coordinate frame attached to it. Now, from now on, whenever we talk about coordinate frame, we're talking about Cartesian coordinate frame. Okay. And what's the length of the axis in Cartesian frame? Unity. But we never discussed the length because it's unity. So we assume 3 unity vectors that orthogonal to each other. That will be our Cartesian. And we call it x, y, z. Or is more friendly. So let's say there is a frame connected to a rigid body, so we know where that body is always from. Now, if we go from this position to, if we rotate through this mapping of 1, this will be a rotation. Now, if we translate through mapping of 2, that's shown by 2, that's where our object would end up. That's a translation. So from this position to the new position, we went through a rotation and a translation, right? So all rigid bodies will have a combination of these two. Could be only rotation, only translation, or consecutive combination of these two. So this is the case for rotation plus translation. Now you have this frame. You know what degree was the rotation and how far you translated. You can find the location of the object in the new place. Now, you might have heard of motion. So we could also create a mapping that if my object was here, my rigid body, I can go through one motion that's called screw motion and end up at the same place. The screw motion, we will learn about it later. But if you're reading your book, you will hear screw motion a lot earlier than I will discuss it. It's basically the combination of those two. So it's like a screw motion, really, like screwing along an axis and with an angle of theta, for example. All right. So this is the case of screw motion, but you can find screw motion using that as routine. Why is this important? Because you're going to create those mappings to know at any time there are. All right. All right. So some rigid body, we talked about it. Rigid body, large form, the definition is either zero or negligible because it's not elastic. Remember that. And we can represent a set of R3. So our Z that are all elements of R, right? Now, it's a single mapping, G, or whatever you want to call it, and maps all the coordinates of the body frame to a frame. Now, since you have rigid body, you don't have to have all the points in that. If we attach the reference frame, if you attach the frame to that rigid body, you can just wherever this frame goes, the whole body must be going there because you don't have elasticity here, correct? So we are simplifying a rigid body to a frame. Whenever I say frame, think of this beautiful arc. Has three axes, X, Y, Z, or Z. You're going to attach multiple of this to different body frames. Good so far? So if I am here and we have a point P, and then for the mapping, we go here, there's P, we can find G such that can find us, if we have where P is originally and we know where G is, we can find a new location. If you have this guy and you have the new place, you can also drive the mapping. You can also transform vectors. What is a vector? So if you had on that like rigid body P and Q, and there's a vector between P and Q, P minus Q, if you rotate or translate, you transform this, the following vector is P prime minus Q prime. This is still the same vector, right? The length of the vector, is it going to change or no? Yes, no? Let me draw that and maybe it helps. So let's say this is the original thing. This is the new frame. This is P, this is Q. Well, God help me if I can replicate this. Let's say this is P, this is Q. So you went here. Do you expect that this is V prime and this is V? If V is P minus Q and V prime is P prime minus Q prime, do you expect the length of V to be equal to the length of V prime or be different? The same, right? Rigid body. The length is not going to change. It's going to preserve the length. The transformation is going to preserve the length part. I'm not boring. Right? So this is one of the important properties of transformation. So remember, rigid body transformation. So we're following rigid body math and equations. The length is preserved. The orientation is also preserved. So if this is orthogonal and I move it, they're gonna still stay orthogonal. They might not be in the same angle. If this was here and I move and it's not in this direction, the angle of each of axes with respect to themselves change, but with respect to each other, they're still orthogonal. So preserve angle, preserve length. The dot product and cross product hold after transformation. Yes. Just mapping. Yeah. So I showed the G for vectors with G hat, scalar with G, but just a transformation. So this box, if this was point P, rotated, this is the rotation, so this is P, and then this is your mapping. You're gonna call that mapping rotation matrix as we go forward later, but for now, you can think of it mathematically just as a mapping. Good so far? Still review of things that you knew before? Like tell us something you don't know. I'll tell you right now. So there are two frames in this picture, right? So we are going to start our motion from here. So this rigid body was here and now is moved that new way. We are going to call this original frame, frame S, frame 0, frame O, whatever you want to call. Make sure that you write it so you know which one was the original frame. So frame S. And I'm showing S as sub of the axis, so I know. Then my rigid body place, I'm calling this frame B. B usually for body. So you usually see it's called B. Frame B. Now, what is this P? What happened to this rigid body? So it went from here. Assume it's the same circle, same oval. So we have two translations, right? Which one is P? Translation, right? What else happened to this rigid body? Also rotated, right? So we have both of them. Now, how do we know rotation happened? Who asked? Who said rotation? How do you know? Your reference frames, the axes, they change. They are not aligned with this one. So if you look, so the original and this is VS. I just moved it from here to here. So that your axis rotated. We don't know how much. We don't care right now. Translation. So P here, the new position of this object was a, and obviously we are measuring it with respect to which frame? So you want to know the new position. If you're in frame B and you measure your XYZ with respect to that frame, what is your XYZ? 0. So you're measuring this translation with respect to the frame that you left, right? So it was measured with respect to frame F. Now the orientation, how do we show that? How do we discuss that? So we have X, Y, and Z axis, right? To show this, you will write the first frame, the frame that you left, you're gonna write as a subscribe. The first frame goes here, F, and then G. So you can call this initial frame and the new frame, whatever you want to call. So we're gonna follow this convention. Now you can see, like, if you're reading some other literature, other books, it could be like B, like ST or ST. Every time you're reading something, you at the beginning they will tell you how they're going to use it. What is the convention? Your book is using subscription. All right, but don't get confused on that no subscription. They will explain which one is the original frame, which one is the frame you ended up. So the orientation is shown as such. The axes And which one was the one you left? Which one is your new axis? So far it's still nomenclature. We haven't done anything mathematically, right? To do that, we are going to create rotation matrix. Because for position, it's just an XY axis measured from the original vector. You don't need to do any discussion, right? You measure it. Now for rotation, it's a little bit more complicated. So we're going to use rotation matrix to describe that. If you are taking a nap, you're sick to wake up. That is the time to listen. Right? I'll always tell you when it's time to listen. Now is absolutely. All right. So for a rotation in plane, you will do plane and then you'll do 3D. 3D is the same as plane, only difference is still having two axes. You're gonna have all three of them. All right. So my original frame here, do you see that properly? Of them. So our original frame is frame 0. We rotate it to frame 1. So frame 0 rotated to frame 1. They're both on top of each other right now. Now, we want to find the coordinate of frame 1 with respect to frame 0. How do we do that? How do we show? Any ideas? If you know this, don't answer. Those of you that don't know, I want to think about it. Does that make sense? You probably know how to do it. Don't say it. Think about it. You know where frame 0 is, and you know how much you rotate it. You know theta. What would you use? How would you represent the frame 1? Think about it like 30 seconds. Any ideas? Yeah. Do what? No, we are gonna stick to Cartesian. No polar. For a very long time, we are writing Justin, you know? Close, but not cigar. Did you raise your hand? Yeah. So you see that now we know the coordinate plane or unity vector is 1, right? Times the cosine or sine of how much they rotate it. It will be equal, right? If you think about x1 as a coordinate, then you can find the value. Now the value is not just find x0 and rotate. You want to project both x0 and y0. So you want to project the new frame on both of the previous axes. So that's the part. So for x, I'm going to take 0 and 1. It means that all frames are the same. We are going to have, looking at this arrow, I want to know what of the new frame on the old frame. We're trying to find the relationship, right? So in the x0 direction, we have cosine of theta. In the y now, remember, it's 1 times cosine of theta because these are unity vectors. So you're not going to write string shifter like that. So this is x0, and this is direction of y0. Now, how about y0 and 1? What would that be? I already found x1, and then I'm trying to find what y1 is. So this is the projection. What is cosine of theta? So this is theta. Now, also have to find what is this? Sine of theta. Oh. The projection in the direction of x0. What is it? What is it? Negative sine of theta. So part of this way, right? You obviously your projection is a negative side. The negative sine of theta. That's what I have said. Right. And then how about the new one, the direction of y0? Cosine of theta, right? So now we will introduce our rotation matrix. We will say that oh, 0, 1, going from all frames to the coordinate of x01 and the coordinate of y01. Which will give you r01 is so cosine of theta and then sine of theta. Boom. R01 is that matrix. That's your rotation. Now, there is another way to find this. What Justin was trying to say. Do you remember we talked about projection, right? In vector algebra, you can find projection of one vector into another through one operation. What's that? Dot product. There wasn't cross product, it was dot product. So we can also show this as dot product on these two axes. So how? Well, this is how. We can say x01 in fact is x1 dot x0 and x1 dot y0. Projection of x1 on the other axis. Now, if this was 3D, like if it was 3D, yeah. What do we have? What do we add to this matrix, to this part? What does the 3D axis have in addition? Z axis. So you have to find the projection of x1 on Z0. That's how you find the 3D. If you have 4 dimensions, go for it. You could add that. But. And then for y, so y1, well, this is not 3D. What would be for the y1? Y01? So y1 dot x0. So if you put R01 is going to be x1 dot x0, x1 dot y0, y1 dot x0, y1 dot y0. Okay. But remember, look at this. Okay, here. Probably better color. So the columns are each axis of your new coordinate. So this is x0, y0, z0 if it was 3D, x0, y0. So this second part is always changing. And the first vector is x because you're trying to find projection. So this is called direction cosine. If you have heard of that before, this is a direction cosine method or projection method. Yes. Yeah. You mean like as x1, x0 sine of theta? What is this not working? Hold on. Yeah, because why? So what is the dot product? X1, x0 cosine of theta, right? Both x1 and x0 are unity. So 1 times cosine of theta is basically the same. Okay, my pen has decided not to work for some reason. So this one is y1. I'm trying to put 1 here. It doesn't work. I'm gonna fix that, but meanwhile. Same thing for 3D, you just have all 3 vectors, all 3 axes, and here x0, y0, z0, x0, y0, z0. So these are the direction cosine for in 3D. Now, the good thing about rotation matrices is that they have some properties that you use them later and they're very beneficial. One of them is that the transpose of them is equal to the inverse. R transpose equal to R inverse because they are belong to a special orthogonal group, SO capital N, but since we are in 3D, in 3, 2, and 3 dimension, so we only deal with SO2 and SO3. So it's R2 and R3, right? And the orthogonal matrix have determinant plus minus 1, but since we are in only right-handed rule, it's going to be 1. So determinant of that rotation matrix is going to be 1. You're not going to directly use it, but sometimes you will use when you're going to prove things. So, it's good to know that you're only going to be. Oh, I know why it's not working. Because it's tipped off. All right. Huh. Oh, do it. Let me fix that. Why one? Why one here? All right. These are the properties. You probably know the most useful for now is that R inverse equal to R transpose, and also that since the unity norm condition, so these are all equal to 1. And if you have the orthogonal condition, which is cross product, is going to be 0, right? The orthogonal, so their cross product is 0 each 2 axes, the dot product is 1. All right, here's an example. Try to find the rotation matrix. If you can do this, you can do a cross rotation. I open the class, the one next, well, next class, Friday, beginning of class. So you have more than 1 minute, but actually you have to review this. Now, first find the rotation matrix for this. Frame 0 is a 2 angle theta about 0 axis. We're going to find R01. You can use the projection method, like the direction program. So I guess those are, this is y0, so this frame rotated to the new frame. I'm going to show the new frame before me. So rotation happened around the axis. Oh, it's fine. This is not big enough. Oh, okay. So let me show you. You're trying to find R01. If you look at a few pages earlier, I've already showed you what that matrix look like. Specifically, this page. here. So you're basically using that. So I'll write the first one. X1 dot product X0, X1 dot product Y0, X1 dot product Z0. So you want to create 3 columns. Now, let's take a look at first one, then it probably will help you finish the rest of them. Now, X1 and X0. What's X1 dot product X0? Oh, this is the, so you're trying to find this distance, right? What's that? Cosine of theta. You still are trying to find the projection, right? This is the projection. The projection of that is going to be cosine of theta. So it's x1, x0, cosine of theta. How about x1 dot product y0? So x1 and y0. This. What is that distance? Sine of theta. Now, if you were going to find, would be x1, y0, and this angle. What is this angle? 90 minus theta, right? If you want to think about it. So that is how that's sine of theta instead of cosine of theta. So one way to look at the distance, like if you find the use the projection. One way is if you actually find the proper angle and do it through dot product. So cosine theta, sine of theta. How about x1 dot z0? 0. Why? There's no projection, right? So that is going to be 0. Now find the other two. If you find, you can raise your hand and you can fill it together. Okay, what is the second column? Sine theta, cosine theta, 0. So it would be y1 dot x0, y1 dot y0, y1 dot z0. So how about the third column? Someone else. 0, 0, 1. So we're trying to find the projection of axis on z, right? And our z is orthogonal to the x and y. So it kind of gives us the clue that, okay, 2 of them must be 0, and the third one is 1 because in the same direction. All right, so this is your rotation matrix. Now R01, cosine of theta, sine of theta, 0, negative sine of theta, this is not delta, cosine of theta, 0, 0, 0, 1. We also can show this by rotation, z and theta, or rz theta. This is the rotation matrix when you rotate about z-axis, always. So basically you will have rotation about all three of our axes, right? And you will know what they are. You just have to remember. Now your class participation, I basically gave you an angle, find the rotation matrix. It should be good, but for your practice, I will say that if you don't know how these two columns came from, do those for your class participation. And if you know, use this to find to solve the class participation. So here's your class participation. The same problem, just theta is 45. Well, when you do that, also I want you to show that the unity is still whole. Unity is still whole for each of the axes. How do we find that? Here, let's go back. How do I show that this is your new X, right? How do I show this is unity? How do you find the length? I know, but how do you get it from here? Mathematically. Progress. Yeah, do you know? You raise your hand, I find your hand. Determinant? No. But really, you guys are answer one question. Okay, go ahead. How do you find length? Square root of cosine square plus z squared is 1. So when you put 45, find and you see that for all of them still is unity. So length is preserved. All right, so when you say length is preserved, it has to be. All right. So I'm gonna save you, and next class Friday, because the only thing is that we have left is 2 examples. We'll post the solution. Go ahead and you review, and I will solve them at the beginning of Friday's class. And these are all the rotation matrices that is possible about X, Y, and Z. These are pure rotation. Yes. Is there submission code? There's no submission code. So this is, I opened it until Friday is the class. So you just submit right now, but there's no submission code either. Let me close this so I can keep your